So, a little about me. I am Josiah. I'm an R&D project manager. I design optical thin films for a variety of applications: aerospace, ophthalmic, illumination, a lot of. It sounds complex, but with a name like this, I needed to be in something complex. But good news is, we being in Pythonistas, there is also an easier way. Everybody calls me Joe, so it's simple as it gets. So that's about me. You can find me on LinkedIn. I used to be a musician before getting into R&D. So I also put up some songs once in a while on YouTube. So you can also find me on YouTube putting up some songs. Is there anybody from Bergamo? Italians? Any Italians? Okay, thanks. There are also songs where I sing in Bergamasque dialect, because an Indian singing in Bergamasque, okay. Because I thought I was mistaken into thinking that was Italian, and I learned that before I learned Italian. So that was the story behind it. And I also have with me Pylock Holmes. If anything goes wrong, it's his fault. So let's get started. Okay, we all know, I'll just run through because I have very less time. Digital files can be divided in two, classified into two: text and binary. Though text is a binary format, you would classify, if it is human readable, opening in a text editor, it is text. Otherwise, if you need a special program to open your file and understand it, it's binary. So today we are going to decode, understand what some program writes the binary data, and you're trying to find out how it is written. I don't want to get all of you in trouble by hacking something, so I just also hacking and getting into legal problems. I also want to discuss a little bit of legality behind this. It turns out that the EU allows the decoding and the reverse engineering of files for special uses. Interoperability is one of them. And there are also other uses like educational, to understand. There are also other uses. My necessity was interoperability, because I had multiple spectrophotometers with their own binary data, binary format, and each of their software, the bundled software which they gave, didn't read the binary spectra of the other spectrophotometers, so I needed, there was no interoperability, so I needed a way to get them all working together, and besides, their software was limited for my application. So I designed a software, but I found very little information about how to understand the binary. So it took a little bit of work, but in the end I got there. So before we start decoding a file, we have to understand a little bit of the properties of a data block. There is something called the endianness or the byte order. It could be either little endian or big endian. The little endian is the least significant byte, comes first, and then the most significant byte. Whereas in the big endian is the reverse. The most significant byte is read first. The types of data are also important, because there could be strings, booleans, numbers as in integers or floats, and the size of the data block, because this is dependent on either the type of data or the precision. For example, a float could have a high precision or low precision. So these are the things that we need to keep in mind. This is just a table copied from. We'll be using the struct library from which is included in the Python. This is just the data copied from that from the struct page. So today we are going to try to decode a binary format using Python. It is a spectrophotometer data. We will use the struct library, Jupyter Notebook. There'll be a spectra in binary format. This, I'm just giving an example of the kind of data that, that I have. It's a 2D data, as in there are two columns. There is a wavelength column, and there is the corresponding transmittance values for that. In this, it is the visible spectrum. We have only the blue wave. We can see that the blue wavelength transmits about 90%, and the green is almost cut, and red is about 90%. So this is only the visible data, but the spectrophotometer can also contain UV and the IR, infrared. I also have, not only do I have the binary format, I also have the CSV files with the corresponding data. So for me, because I own the software, I use the software to export the CSV files, and then I'll use that to decode the files and then try it on other files. Okay. Now I'll show you the. Okay, this is my folder. This is my folder. I have, as you can see, bottom 5 files are the spectrophotometer data. If I try to open it with my text editor, as you can see, it's all gibberish. So it is binary data. I can't. It's not humanly understandable. I have the corresponding values in CSV files. I'll use 3 files, 3 spectrophotometer data to try to understand if there is a pattern, to identify a pattern, and then I'll use the pattern if I manage to identify it, and use that on the other 2 files to see if it works. So let's get on with the Jupyter. I have already typed everything because for the lack of time. Okay, this is my I just load in the data, and I'm just loading in data of the data which I got from the struct info page. This is the web page of the struct library. There is a lot of information about the endianness, which characters to use, because that the struct library can understand it. So the length of the if you're using a C type, say you're using the int C type, it's 4 bytes length. So those kind of data I'm just loading into, and I'm just loading into my dict for using afterwards in the program. The data frame is just used to display, nothing else. So I have, as I told you, I have everything in this folder. I'm just going to load in, for the sake of simplicity, everything into this variable. I'm just using glob to load a list with all these file addresses, and so it'll be easier for me to access to load in the data. So first I'll take the first 2, which is 0. The index 0 is the sample file CSV sample file. Index 1 is a binary file, corresponding binary file. I'll take 0 and 1 and load it into an integer, which I'm just using as an index. I'll use pandas to load in the CSV file to a data frame. I'll get the the number of data points. And so this is it. I've just taken in the CSV, all the data from the CSV into the memory. I'll plot it. This is the spectra, just the plot of the spectra. But while plotting it, I've also loaded the 2 columns into 2 variables for use later. And now I load in the binary data. I'm using the index which I'd saved before, 1. I'm using RB to load in the data as a binary. And I'm also checking the number of bytes in the data. It contains 1324 bytes. I've saved it onto a variable, also that. Okay, now let me take the first 5 values and try to find out if I can locate it in the binary file. I don't know the endianness, so I'll loop between the 2 endianness. This is the little endian, this is the big endian, these are the strings that struct uses. And there are, I'd seen that the values were all floats. There are 3 float possibilities, as you can see from here. These 3 are floats. So I'll just loop between those 3. And then I'll scan the whole binary file. The way I do it is something like this. Let's say this is the binary data, and I'm searching for this small binary block. The first iteration at the 0 address, I take 8 bytes and compare it with this, not found. Second iteration, I take the first till I find it. So at this point where I find it is byte 3, not address 3, Pythonic address 3. This will be printed, but I won't stop there. I'll continue till the end of the file. I'll tell you why a little later. I use print statements a lot for this because Python print is green. And I love it. No trees were destroyed. So, and it also is easy here. This is not going into production. So I know all you Pythonistas are against print. Yeah. So I ran it. As you can see, it found values with little endian and with F only. The other values it didn't find. So I'm quite sure that it was little endian and F. So now I can scan for the whole file to see if all the values I can find. I hope everyone is with me till now. Okay, because I'm trying to go fast and I'm not sure. Okay, now I'm going to scan everything. And it found everything. So it found everything. One thing which I note, it starts at 120, the byte address 120, and the last value found was at 1320. This we'll need later. The same thing I'll repeat for the wavelengths. As I told you, it was a 2D data, the wavelengths. I'm just trying for the wavelengths now. I'll run. It didn't find most of the values, but it found the first and the last. Okay. Anyway, 10 and 14 were the 2 values which it found. Okay, we'll try to save it all into a default dict. 10, the highest wavelength was found at 10. byte address 10. The lowest wavelength was found at 14. The value at the highest was found at 1320, and the value at the highest wavelength was found at 120. So I'll just load it into a dict. With one, you don't have a pattern. So let me try with the second, see if some kind of pattern emerges. So again, I'll change the indices. I'm just taking the sample 2. I'll repeat the whole thing. I'll plot it. I'll read in the binary. I didn't need to do that. Okay, let's see the wavelengths. Again, 14. Let's not see. And 10. Here 720 was the lowest, and 120 again. This has been repeated. So let me save these. It was 720, everything else was the same. I'll just load this in. Now we seem to have some sort of pattern. I'm not doing the third one for the lack of time, but I know that the pattern is already there. So let me print out, let me view this. It always starts at 120. This seems to, the values always start at 120, and it seems to go till the end of the file. And the lowest wavelength is always at 14, at byte address 14. Highest wavelength is always at byte address 10. Let us see. This is we don't have any intermediate wavelengths. We don't have the spacing, because the spacing of the wavelengths could be different. It could, in this case, it is 1, but it could be different. So, and the transmittance values always start at 120 and continue till the end. But the number of points can be gotten because we know that the transmittance values are starting from byte 120 and go till the end. We can already calculate the number of bytes. This is how we calculate the number of bytes. The number of data points, sorry. I've calculated the number of data points here. See, so it corresponds with the value that I found in the CSV file. This was what we had input in the beginning. So we have found something which could work. We have found a pattern. Let us see if it can be applied to those other two files which we didn't. We'll load in directly the other two indices which we'll load in the binary. Let us try to load in the wavelength. It is different from the other wavelengths. The highest wavelength. We load in the lowest wavelength. The number of points is how we calculate it. 120 divided by the total number of bytes by 4. 4 is the number of bytes. For the values in the list, I'll have a loop. I created an empty list and I appended all the values, and I'll use an NP linear space to sort of, I know the number of data points. I can space out the wavelengths and find all the wavelengths by that. And now we'll compare the two by plotting. I'll also load in the CSV, and we'll compare if it if it matches. It's a perfect match. It's one on top of the other. For those, if you have any doubts, I'll also, since all the values were reversed, so I just used a reverse. And if I, these are the two values put next to each other. So you can see that we managed to decode a binary file in a short time. Actually, this, a binary file, I'm just telling this for you, can also contain headers, data blocks, block in identifiers, and junk data. This is just for your information in case you want to. Any of you have the need to use have the need for decoding files, or okay, okay? I thought I was misfit in this PyCon. Okay, I uploaded the Jupyter at GitHub today morning, and thank you all. Thank you all.
Thank you very much. This was very insightful. So please keep your questions coming. So there's a question here. In your case, what is the advantage of reading binaries instead of CSVs?
In my case, to export the CSV in the file, in the spectrophotometer software, it was an operation which I had to do it manually for each file. Whereas when I saved the when I ran the scan, it saved it automatically into the binary format. And not only that, the binary format, it made sense always to have the binary format because the binary format also contained many other, in this we saw only the spectra data, the 2D data. It also had other parameter, the binary data also, there's 120 bytes, also had scanning interval, it also had the parameters, scan speed, it had other parameters which were not, I managed to decode it later, but I didn't present it. It also had other parameters which a CSV file didn't have. So I needed to decode the binary file and then use it.
Okay, great. So does anyone else have any question? Okay, so while we wait for more questions, so I have a question. Can you share with us any challenges that you faced using this method?
Okay, since we have time, I'll show. The first time I got mad because I didn't understand what was happening. You'll see in the code. You can see this abs temp. I'm sorry. Temp. I'm not checking if the value is equal to the wavelength of CSY, but I'm seeing the difference is under. I went mad because I didn't it didn't find. I found out later it is due to one thing called now the name doesn't come, but just to give a. I'll give a small. If I had to. What would you expect the answer to be? Oh, sorry. I'm sorry. Is okay? I would expect it to be 0.01, right? Oh, why didn't it? Okay, because I didn't. Because this is something which is, the machines understand binary, and decimal is not, we understand decimal better, but when there is a conversion, it is not exact. There is a little bit of difference between truncation. It's a sort of truncation, but there is another word for it which doesn't come to my mind. So this was what was happening, and I didn't understand. This was in the beginning when I didn't have any information on the web when I started out. So this made me mad.
Okay, great. So
challenges every when you decode anything, it's always a challenge.
Okay. Sorry, I'll get back. There's a question here. Okay, how could you deal with encryption in the binary file?
Encryption?
Yes.
That is a lot of trial and error, because if somebody wants to really encrypt a file, it is hard. It's a lot of trial error. Usually, till now I've decoded about 6 spectrophotometers and some other files. I've always been able to do with this, but for I tried encryption on my own, and it will be very, very hard to decode those kind of files.
Okay, sure. And your hand was up. Okay. Any more questions? Okay. Thank you very much. This was insightful.
Thank you.